Swayam Prabha. Digital India. Educated India.
Hello all, welcome to Astrochemistry. This is lecture number 56. So in the previous lecture, I had introduced you to the problem of modeling rotational motion of diatomics, right? Diatomics. This is as part of understanding molecular spectroscopy, and the model we used was what is called as the rigid rotar model, right? Wherein two spherically symmetric masses were connected by a rod. The system does not deform, right? In other words, the length of the bond while we model the diatomic is going to be a constant. And then we started off writing the time-independent Schrodinger equation for this molecule, for the system of the rigid rotar. And I told you that we had to convert the Cartesian coordinates into the spherical coordinates for ease of solving the problem. And so after that, we could obtain the wave functions and the energies of the system. Okay. Now, the energies were obtained using what is called as the boundary condition. And I had given you the analogy of the boundary condition in the case of the electron whose motion was restricted between, any two potential barriers. Okay, right? So the boundary condition for this problem is as follows. Now, that's what we'll be beginning this lecture with. Okay, so the boundary condition for this problem, the boundary condition for the rigid rotar problem, if we're going to model the rotation of diatomic molecules, is that after every rotation, right after every rotation, you get back to the same position. Do you understand what I'm saying? Because that is the essence of rotation, right? Let's say you start rotating from any one point, and after you rotate, you get back to the same point, right? The same point as defined by the r theta phi. Okay. So that is going to be the boundary condition. And after using this boundary condition, I'm going to be skipping the mathematics. Okay. After using the boundary condition, you get the wave function and you also get the energy. The energy you get as J into J plus 1 times h squared by 8 pi square I, where I is the moment of inertia. I already told you that effectively for this diatomic molecule system, we'll only be having one value for the moment of inertia. Okay, right? And where J is any integer, okay, any integer starting from 0, 1, 2, etc., etc. All right, are we all good? Now this is a very important expression. Please note it. So how do we get this expression? We get this expression after applying boundary condition to the rigid rotar problem. The math I have completely skipped because this is not a quantum chemistry course, and the math would involve, essentially some 30 minutes to 45 minutes of solving this problem. So let us not spend that time here. All right, it is a very well established problem. So therefore, my energy is given by this particular expression, E is equal to J times J plus 1 into h squared by 8 pi square I. Now, having obtained the energy, and notice this. Now, this J is an example of a quantum number. Recall that we've already seen quantum numbers in the context of the electron whose motion was restricted. And I also told you that, when we discuss hydrogen atom problems, right, the quantum numbers arise as a result of another boundary condition over there. Okay. So quantization always comes. This is also quantized, right? Why is it quantized? Because only certain values of J are allowed. J cannot be, 3.14. J cannot be 2.72, for example, right? So J has to be integers, right? And on top of being an integer, the energy has this following expression. Okay, so therefore this is an example of quantized energy. So this quantization arises as a result of the boundary conditions imposed. This is a fundamental feature of quantum mechanics, which is time and again going to be seen in spectroscopy as well as into astrochemistry. Okay, so we now have this expression. Now let us manipulate this expression. Now this expression can also be written as E is equal to Bj times j plus 1, where my B is what is called as a rotational constant. Okay, right? So E is going to be called as a rotational constant. And also note that this J also is called as a rotational quantum number. Okay, let us now briefly focus on the units and dimensions of the various quantities in these expressions. Let me call this expression 2 and this is expression 1. Okay, now the left hand side is of course energy. Okay, so therefore the right hand side also has to be energy. Okay, right? And J is just a number. It is a quantum number, right? It's a number, so therefore J has no units. Therefore this entire thing, h squared by 8 pi square I, has to be having units of energy, correct? So in this modified expression where E is Bj times j plus 1, therefore my B should have the same dimensions as energy. And what is actually B from this expression right here? My B is nothing but h square by 8 pi square I. Okay, now even though B has energy units, right, it is often expressed in terms of both energy units, in terms of frequency units, in terms of wave number, that is the inverse of wavelength, and in rare cases even as wavelengths also. Okay, right? Let us look at all of them now. Let's just ensure that B actually has units of energy. So this is h square, so this is going to be a joule square second square, right? And the moment of inertia, what is going to be the units of moment of inertia? Well, I told you in the previous class that it is the equivalent of mass. But is it just the mass alone that comes about? Is it just mass unit? Do you remember? Well, from any expression, tau equals I alpha, L equals I omega, and all those things. Or the generic formula, I equals mu r square, right? So from that, the moment of inertia using this formula for a two-body system, right, of r square, where mu is the reduced mass, and r, is the effective distance from any of these bodies to the center of mass. Okay, so my I therefore is going to be given by a kilogram. That is like I'm just going to call it as mass times length square. Okay, so now this has to be converted to mass and length, right? So that is going to be, now joule is going to be what? A joule is nothing but E, if you use E equals half mv square, this is going to be mass times v square, that is L square s to the power minus 2, right? S to the power minus 2, the whole square times second square, right? Now, therefore, this is going to be m square L to the power 4 s to the power minus 4 and s square here. So therefore, this is going to be s to the power minus 2, and this is going to be m L square here, right? You see what I'm doing, right? I'm simply expanding upon the dimensions. So then this becomes L square, this becomes m. So this is effectively m L square s to the power minus 2, which is the same as energy units. Okay, so B indeed has energy units. All right, energy units and dimensions. Now, oftentimes I'll delete this part. So B, right? Okay, this B is not just measured. Okay, is not just measured in energy units, for example, say joules, etc., but is also given as centimeter inverse corresponding to your wave numbers, and also let's say second inverse of some variation of frequency. Okay, right? That is new. And on very rare occasions, they also take the reciprocal of this to give it in terms of lambda. Okay, that is the wavelength itself. So how is that done? How is this converted? Once you have, like your the energy of B in energy units, how is it, for example, converted into per centimeter inverse and per second? Straightforward. Let's say, take B. You start with B in joules. Okay, in SI units, given by h squared by 8 pi square I. Okay. Once you get this, now divide both sides by the speed of light, right? And you use the idea that your E is equal to hc nu bar, right? So therefore, if you're going to be dividing both sides by C, right? What's going to be noticed here, right? So if you take the RHS unit, this is going to be it's effectively going to be joule per, or I'll use the dimensions. It's going to be m L square s to the power minus 2, right, divided by Ls. That is like, it's C over here, right? So this is going to be velocity. Velocity is nothing but like Ls to the power minus 1, correct? So now that we have it, this is effectively going to be m L and s to the power minus 1, correct? Now what is this? Your ml s to the power minus 1. What does this correspond to? This corresponds to E by C. Okay, right? E by C. Now, if you actually were to divide this by units of h also, right? Let's say you divide this again by h. So if I now were to divide both sides by h after dividing by C, I have to divide this quantity divided by the dimensions of h. Note a quick point. See, I mean, for time alone, right, I should be using t, but instead of time, I'm just using it in seconds, okay, right? So please forgive me for that. So for time, instead of t, right, as is conventionally used, I'm just using s, to mention it in seconds. I've just started using it, so I don't want to go back all the way and do some manipulation. So I'll just continue using s, noting that for time I'm using seconds. Okay, please bear with me about this. All right, so now I have to divide this quantity by the dimensions of joule second. That is going to be m L square s to the power minus 2 s to the power minus 2 times s to the power times a second. Yeah, right? So this is the mass get cancelled out, and then this is s to the power minus 1, and this is going to be s to the power minus 1 effectively. So they also get cancelled out, and I'll be having length by length square, which is 1 over L. In other words, I'll be getting the units of nu bar. So this can be measured in centimeter inverse. You see what I did, right? So I started off with B in terms of energy, right? And once I get it in terms of energy, I can measure it in terms of both centimeter inverse, right? Or now that I have some value in centimeter inverse, I can manipulate it to get it in hertz also, correct? That's straightforward. I'm just going to simply use the formula, right? C equals nu lambda. So from here, I can easily get the value of B, right, in frequency also, all right? So, this portion now looks reasonably ugly after the rough work that we did. Okay, so I'll just sum it up here. It is that the rotational constant B, right, can be expressed as B by HC, that is in nu bar, right? Or also, or also in terms of frequency, that is like hertz. Okay, right? I'll leave it to you as a homework. How to convert? Homework. B in joules. I'm just calling this B dash, okay? Just so that you don't confuse between the two symbols. To B dash in terms of frequency. Just like, we did it in terms of wave numbers, all right? So all of this can be done. Now, this rotational constant B, okay, right? This rotational constant B is, I cannot understate this statement, okay? It is extremely critical and important for not just the detection of molecules in space, okay, for both detecting molecules in space and also identifying them on Earth. And also identifying them. By them I mean molecules. Okay, so this is a very, very, very important point. This is, in fact, this is the crux of the application of spectroscopy to astrochemistry. Okay, now let us look at how B is precisely applied in the context of astrochemistry. Okay, one way, one of the very first applications of B in astrochemistry is that we can define what is called as a rotational temperature based on the rotational constant B. Now let's say you measure B in frequency. That is like in frequency units. That is, let's say you have it as some inverse time unit. Okay, right? You measure B in time units, and if you consider this quantity, HB by kb, okay, right? Now what is the dimension of this? If you consider my units, right, H is going to be in joule seconds, okay, right? And if I measure my B in second inverse, can it be done? Of course, yes. Although in the class I showed it in terms of the wave numbers, I had given to you as a homework that you can always convert the wave number to frequencies also. So you can do that on your own. So B can be expressed as centimeter inverse, or like, sorry, second inverse. Centimeter inverse is the wave number 1, and second inverse is the frequency 1. So your B is going to be in terms of second inverse, and my Boltzmann constant. What is the unit of Boltzmann constant? It's R by NA, right? So R is going to be PV equals nRT. So R is going to be PV by nR. So that is joule per mole per Kelvin, and Na is going to be per mole. So this is going to be joule per Kelvin. So if I have all of this, the joule and joule get cancelled out. The second and second inverse get cancelled out. This is 1 over Kelvin. So this is Kelvin. So if you notice that this quantity HB by KB, when B is measured in frequency, okay, right? If B is measured in energy units or something, this expression is going to be slightly modified. You can work out the arithmetic yourself. That's not going to be hard, okay? But once we know this, right? This has dimensions of Kelvin, that is temperature, and this temperature is what is called as the rotational temperature of any molecule. Okay, please note this point. So this rotational temperature is actually a measure of, okay, it's actually a measure of the temperature at which, okay, the temperature at which the thermal energy, okay, right? The temperature at which the thermal energy is of the order of, I will continue there, okay, is of the, so what I've written is the T rotation, that is the rotational temperature, is going to be the temperature at which the thermal energy of the system is of the order of, I'm continuing right from here, okay, right, is of the order of the difference in energy between any two successive rotational states. What do we mean by this? Let's say that if my E1 equals B times J1 times J1 plus 1, and my E2, right? See, the rotational constant doesn't change between any energy level, okay, right? Times, there's going to be no times because everything I've expressed in terms of B already. This is going to be J2 times J2 plus 1, right? Where, let's say J2 minus J1 is 1. In other words, I'm talking about any two successive rotational energy states, okay, right? This delta E, which is given by modulus of E2 minus E1 or E1 minus E2. I don't care, okay, for our purpose. Now this delta E, right? The rotational temperature is a measure of this gap here. T rotation is a measure of this. All right. Now, have we seen this concept rotational temperature somewhere in this course? I briefly, alluded to the phrase rotational temperature, right? Although did not give you many more details. When I actually was talking to you about the very first detection of molecules. What are the first few molecules to be detected in space? CH, CN, and CH plus. I mean, probably in lectures somewhere in the mid-20s, I believe. Okay, right? Or maybe early 30s. Now, back then, I told you that based on the rotational transitions, right? The rotational transitions in electronic spectra, right? As part of electronic spectra, one can find out the temperature of the interstellar medium. I told you, right? Now, I also told that, most strictly speaking, it should be the rotational temperature, but I avoided using that phrase. Okay. Now we understand that from the rotational lines, that is from the rotational spectra itself, by calculating the energy difference between any two levels. Okay, right? Because that can be expressed in terms of B. We'll see that in just a few minutes. Okay, because we can always express delta E in terms of E2 minus E1. Therefore, we can get an expression in terms of B. Okay, so my B is a measure of the spacing between any two energy levels in the rotational spectra, and that the thermal energy corresponding to that is given by this T rotation. And what did we see was the value for Cn? Recall from an earlier lecture. I will delete this part and you recall from lecture on detecting Cn. By who? By Andrew McCullough. I think I have used the phrase AM to abbreviate his name, right? Detecting Cn, the rotational temperature. The temperature I told was found to be approximately 2.7 Kelvin, right? That actually corresponds to your rotational temperature. Okay. Now you go back to that, this particular lecture, and I may have used the phrase, rotational temperature. I may have skipped on the rotational part, but that is what I mean when folks or people say that they're talking about the temperature of any medium, part of the interstellar medium. Okay. So rotational spectroscopy can give you very powerful information about the temperature in the various parts of the interstellar medium. All right. So now you get back to the idea that my delta E, right? My delta E can always be expressed in terms of B, the rotational constant. Okay. Now let's just write this expression. Okay, right? If when my let's say that my J2 minus J1 is 1. Okay. In that case, my delta E is going to be B times J2 into J2 plus 1 minus J1 into J1 plus 1. So if my J2 is nothing but J1 plus 1, okay, right? That is like if J2 is J1 plus 1, this is going to be B times J1 plus 1 into J1 plus 2 minus J1 plus 1 into J1. Now if you take out the J1 plus 1 outside, I have my B here. This is going to be J1 plus 2 minus J1, right? And so this is simply going to be 2 times B 2 times B 2B times J1 plus 1. All right. So therefore, the energy gap between any two successive levels, right, of rotational transitions is simply given by the product of J1 plus 1, where J1 is the quantum state from which the transition is happening, and my B is the rotational constant. Okay, are we clear? So please note this idea also, that I will delete this part. My rotational constant B is useful in getting the energy levels, the energy level difference for any rotational transition. All right. So please note this. See, now this is going to be particularly useful because now let's say, okay, right? Let us say that my J1 corresponds to 0. Okay, right? Say, right, J1 corresponds to 0. In other words, I'm starting from the ground rotational state. Say that all my transitions are happening from the ground rotational state. Then what I'll be getting is that my delta E is nothing but 2B. All right. So please note this point. Okay, my delta E is going to be 2B. Similarly, okay, right? Similarly, I'll leave it to you as a homework. Okay, right? As a homework, find delta E, right, for the J equals 1 to J equals 2, and delta E for J equals 2 to 3, right? And delta E for 3 to 4, J equals 3 to 4, etc. Okay, do this homework, and this is going to give you a very important result. The result, right, is what I'll be starting with in the next class. So what did we do in this particular class? We started off with understanding what the boundary condition was for the rigid rotor problem, right? And based on that, we obtained an expression. Although I did not derive it, I told you we can completely skip the math in the interest of time. So after we obtained that, we saw that the B, we obtained an expression in terms of what is called as a rotational constant B times a quantum, a rotational quantum number J, right? So J times J plus 1 times B. And then we saw that B can be expressed in terms of either energy units or wave number units, or also, as like frequency units. Although the frequency part, I gave it to you as a homework. Then I taught you about this concept of rotational temperature, wherein, the T rotation is a measure of the thermal energy associated with the energy gaps between the various states, the various rotational states. Then we looked at an expression for delta E in terms of B, right? And I stopped by saying that when J1 equal to 0, right, the expression for delta E is going to be 2B. And I gave you the homework of finding delta E when the transition happens from J1 equals 1 to 2, 2 to 3, 3 to 4, etc., etc. All right. On that note, we end this lecture, and I'll see you in the next class. Thank you.